This is e-homework number, what is our e-homework tonight?
26.
26?
26.
Okay, then that's 26.
Much work did you show on this? That's all I
That's 27.
Okay, e-homework number 26, and it's problem number 5, and it looks a little something like this. You've got a battery, you've got a resistor here, you've got another another resistor here, you've got another resistor here, and then you've got like a switch that can swing from this point to this point to this point, where this is like that, okay? And so you have a switch that can be thrown from point A to point B to point C. All right? And here's the EMF of the battery, resistor 1, resistor 2, and resistor 3. Okay? And the question is this. You begin with the switch in position A, like that. Okay? And then they tell you, you throw the switch from position A to position B, and they want to know what happens. They want to know what happens to the current in resistor 3, is that correct?
Yeah.
Okay. So first of all, let's put our ammeter in, just so we can see it. Where would I put my ammeter so that it would read the current through resistor number 3?
Right before it, right after it.
Okay? Anywhere from here
See the line down.
to here, right? Because that is one line for which the resistor's in that line and the current can't go anywhere else. So I'm just going to put it right down here because there's not a lot down there. Okay? So it's nice and convenient. So there's my ammeter. Now if I wanted to hook up a voltmeter to measure the voltage across, or just the voltage difference from one side to the other side of the resistor. Now remember, there has to be a voltage difference across the resistor, or otherwise you won't get current to flow, right? If the voltage on one side and the other, the potential here and the potential here are exactly the same, then no current, right? So you have to have a difference in volts, right? So how would I hook up my voltmeter to measure the voltage? Now you can hook up one side and then the other, right? In parallel. Because remember, this measures the difference in volts, so therefore one side's got to be connected to a different point than the other. All right, now, they want to know the current through resistor 3. So how would I find the current through resistor 3 mathematically? I use V equals IR. But I want to know the voltage for resistor 3, the current through resistor 3, and the resistance of resistor 3. Seems kind of redundant, but, right? These all have to match up. So that's the current through resistor 3, that's the voltage for resistor 3, and there's the resistance of resistor 3, right? Now, they want to know how the current changes, so I'm going to rewrite it. I equals V, that's a delta V technically, over R for resistor 3, and resistor 3. Does resistor 3 change when you throw the switch?
It's the same resistor.
The same resistor. So what's important? If I want to know that if the current changes, how the current changes, I need to know how the voltage changes. Get out your crayon. If I was to color this, actually the crayons are right over here. I'm sorry. All right, if you want crayons, you can come get them. All right, so pass them out. Hey, if I was going to color this circuit, what does it look like when the switch is in position A? It looks like this, right? Red, 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 red. Red down here. Red, red, red. Technically red down there. And then red all the way to here, right? Because that's the wire that it shares its potential with. Okay, we're using violet, right? So let's use violet. Okay, violet. Violet, violet, violet. Violet, violet, violet. Violet up to here. Violet all the way through here. Violet all the way to there. Okay? And when the switch is in this position, then I'm going to have some color in between right here, correct? So this would be like yellow or green. something other than red and violet, right? Okay, now, look. When I throw the switch from here to here, what happens? When I throw the switch from here to here, what happens?
You have no current flowing in there.
First of all, I have no more current flowing through here. Hey, if I have no more current flowing through here, what color does this side of the resistor have to be? It's got to be something.
The same color.
Why does it have to be the same color?
That means there's no difference, so nothing's going to...
Yeah, it's got to be the same color because otherwise current would continue to flow, right? So what happens is a tiny bit of current flows through the resistor and charges up this side of the wire or the resistor on this side until it's the same potential. And then once it's the same potential, then no more charge flows. Now, how quickly does that occur? Really fast, right? As far as we're concerned, instantaneously fast. And then, so what color is this side of this resistor?
Purple.
It's got to be purple. So all of this is purple, right? Because I have no more current flowing through here because it's got no place to go. There's not a connection between there. Okay? So no more current flowing through this section. Just like there's no current flowing through this section, right? Because it's just a wire hanging out there in space, right? Hey, but did this red and this purple change? No. Then that means that the resistance stays the same when I throw the switch. And the voltage stays the same when I throw the switch.
So the current has to
So the current stays the same when we throw the switch.
Well, basically, because they're in parallel, wouldn't you automatically assume the voltage is constant?
Okay, now that's a really good point. Now everybody listen up. The question was, look, if we drew this not so complicated and we did this. So the circuit looks like this, and what we do is we just disconnect this right here. Okay, we open a switch right there. Because this one's in parallel with these two, does opening that switch do anything to that one? Nothing. That's like in your house. You throw a switch in one room to turn off the lights, but the lights in the other room
Stay the same.
don't go off, right? They stay the same. However, I need to redraw this in black so that we can color the circuit. You need to be a little bit careful about this because what if we have something like this and I have a switch right here that I open? Okay? Okay, now look, when this is closed, I have a certain type of circuit. I have a combination circuit, right? When I open this up, what kind of circuit does it become? Just series, right? Okay, so we have to be a little bit careful because this problem that looks like this is not the same. This resistor right here will not get the same current if I just disconnect this part right here as when I have that down there. Okay? In fact, let's take a look at a problem like that real quick. Okay? Here's our battery. Here's resistor number 1, resistor number 2, and resistor number 3. Okay? Well, why don't we say this is a 12-volt battery? Why don't we say this is 2 ohms? Let's say that this is 8 ohms and 8 ohms. Okay? No, you know what? Let's not do that. Let's do
9.
12. Here, we'll do, I think 9 ohms and 6 ohms will work pretty good. All right, hopefully my numbers aren't going to be too wacky. Here, we'll make this 12 ohms and we'll make this 6 ohms.
It was 6
Yeah, you just erased it and rewrote 6.
What I want to know is, I want to know if I put an ammeter right here, what will this ammeter read? Call it ammeter number 1. I want to know what ammeter number 2 will read. I want to know what ammeter 3 will read. And then I want to know if this is point X, and this is point Y, and this is point Z. I want to know what delta V is from X to Y, and what delta V is from Y to Z. I just want the magnitude. I don't care if it's plus or minus. Okay? So I want to know the voltage difference between these two spots and between these two spots. Okay? So essentially what I'm asking is, if you hooked up a voltmeter between here and here, what would it read? Hook up a voltmeter between here and here, what would it read? Okay? So let's start off simple. Everybody color the circuit to get a feel for what's going on. Okay, so I got red here. Where does it stop being red?
At the 2 ohm resistance.
Right up here at the 2 ohm. Okay, let's work backwards. Violet.
All the way
The 12 and the 6.
yeah,
To here?
through that. It goes through.
Okay, it goes through. Now our meters, in theory, our meters don't do anything to the circuit, they just measure. In reality, they do mess up the circuit a little tiny bit, but we're going to assume they're nice, perfect meters. It goes from here to here, all the way to here.
Every time that happens, I use that.
All right, so here we go. What other color do we have then? Colors.
Yellow.
I don't care. Yellow, green, something, right?
Yeah.
Something else. I'm going to use green this time, just because.
You have green.
I have green in my hand.
Color for attention.
Green rocks.
Yeah, green.
Okay? There we go.
This is talking about.
Yeah, I do that.
All right, excellent. So, the voltage XY will be between green and purple, and the voltage YZ. Okay, we had a very excellent comment. The comment is since these two have the same exact voltage, green to purple, then if these were the same resistance, would they have the same current?
Yes.
Answer is absolutely yes. Sorry.
Wow. This
Oh,
is really
clowning
popular
around.
today, huh?
No, sorry. Hang on. Let me take care of this.
Yeah.
Everybody, how do these two compare?
Green. Okay. XY.
They're the same.
Yeah.
They're exactly the same, right? Because that is the same as that. Green to purple, right? So I just have to find one of them. All right? Now, that is awesome. Now, that tells us something really cool. What that tells us is that if I hook up a voltmeter between these two, that's the same as the voltage difference between here to here, or between here to here, or between here to here, right? So if I find the voltage difference for this resistor, or that resistor, or from this side of the battery to this side of that resistor, it's all the same, right? Okay, here's the first thing I want you to do, is when we have a problem like this, if we want to know these currents and these voltages, okay? We want to know these currents and these voltages. Like for instance, I want to find this voltage from here to here. Well, that's the same as, these are the same, but let's see, wait a minute, Y to Z. Marker dead. This is the same as the voltage for the 6 ohm resistor. It's the same as the voltage for the 12 ohm resistor, right? Can I calculate either of these two?
You don't have. Yeah. Yeah. Yes, you can.
Because I need to know I times R, right? Do I know the resistance of either of these two?
No. But
Sure, I know that 12 or the 6, right? But I need to know the current through here or through here, right? Let's write this properly. Let's write this properly. This is the same as the 6 ohm, which is the current through the 6 ohm resistor and the resistance of the 6 ohm resistor. Okay? Which one of these is the current through the 6 ohm resistor? A3, right? I don't know A3. Right? And if I did this same thing for the 12 ohm, would need to know A2, right? Okay, so here's the deal. Everybody, I know that. I know that. But I don't know this one in either case, so I can't find either of those, right? So, when you have a system or a situation like this where you've got more unknowns than you have knowns, where do we begin? We cry first for a slight time.
And then
We cry for a little bit, and then we decide, you know what? I do know how to simplify my circuit. So I'm going to take my circuit and I'm going to make it simpler.
find our
Ooh, nice arrow.
Thank you. So if I simplify this circuit, what part can I simplify?
parallel.
I got a parallel section here. Wait a minute, how come this 2 and this 12 are not in series?
Because they're parallel without
Because the current through this one and the current through this one
not the same.
are not necessarily the same, right? Because there's a junction in between, right? So series only if they have to have the same current. Hey, is this resistor and this battery in series?
Yeah.
If I had another resistor down here, if I just put one in right here,
I think so.
would this resistor and this resistor be in series?
With
Yeah.
those two still?
With these two still here?
No.
Here's the key thing. In series, what's the hallmark of series?
Same current.
Same current in each device. Does the current that goes through here have to be the same as the current that goes through here?
Yeah, it's the same. Yeah,
Does it have anywhere else to go?
no. It's the same.
It's the same, right? So these two would be in series. So does this ammeter read the current that goes through this resistor? Yes. Okay, they're in series with each other. All right, let's get rid of that. Okay, I want you to simplify this circuit. First of all, draw it without the parallel, and then draw it with only one resistor. Okay, when I add these two together, the parallel piece, what does that become? It's 1 over resistance in parallel equals 1 over 12 plus 1 over 6,
Which is 1/4, so
1 over
resistance is 4.
which is 1 over 4, and so resistance in parallel equals 4 ohms.
So 4 plus 2, 6.
Okay? Now, everybody, or your calculator. A real easy way to do this. Everybody get your calculator out quick. It's a very fast way to do this. Are you ready?
He's gonna show.
Everybody press 12, and then this key,
Inverse.
plus 6, and then this key,
That's the way I do it.
and then equals, and that should give you 1/4, right? Because that's this, 1/12
The inverse of the
plus 1/6. That's inverse of 12 plus inverse of 6 equals, but I don't want that, right? And then after you press that one, press this key again, and then press equals. So you're inverting your answer to give you 4, right?
Or 12 times 6 over 18.
All right.
This is meant to be persistent for this time.
Hey, everybody. Let's not forget that we can color this circuit if we want, because sometimes that helps us out. Where's the red part? Red, red, red. Green. What's the violet part? Violet, violet, violet. Hey, what color is that?
Whatever you want.
That's the same as this part, right?
Well, no.
Isn't this the same as this green here?
Yes.
So it's still green.
I guess.
Green. Okay, now. Why is that still green? Because this Y spot right here, I'm losing some of you. This spot Y is now right here. This spot X is right here. And this spot Z is right here. Okay? Okay, now, let's sum this up. This is series, correct? So series looks like this. I now have my battery, and this becomes 6, because I just add them up. Ooh, if I color this circuit, what does it look like?
Just red and purple.
It just looks red and purple. Okay, where is point X?
Right there. where it's
Same
still
corner.
frozen is
Where's point Y?
gone.
Point Y is gone. Point Y was in between these two that I summed together, right? So point Y is not in existence here. Is point Z still here?
Yes.
Yeah, point Z is over here. Okay? All right. Now, so what good is all this that I just did?
X and B are the same.
In fact, hey, are any of our ammeters still here?
Yes.
Where's my ammeter on here?
Right there.
This is ammeter number 1 right here, right? And ooh, is 2 and 3 there?
No, those are.
Because their lines have disappeared, right? So 2 and 3 are not in this one, right?
Because it's still in the bottom, the last one.
Okay.
A1.
Is any of them still here? Is A1 still on here?
Yeah.
A1's still down here, right? Hey, that's kind of cool, because now look what I can do. I now have my total simplified circuit, where I can use V equals IR for the total circuit. What's the total voltage in my circuit? 12 volts. What's the total current in my circuit?
A1.
I don't know, but it will be A1. What's the total resistance of my circuit? 6 ohms. So what is the total current?
2.
2 amps. So A1 equals 2 amps. Right? Okay, now let's go back here. Now let's work backwards. If I work backwards from here to here, do I know the current in this circuit? I know A1 because, see, this circuit is the same as this circuit. This is one loop, this has one loop. Therefore, the current through here and the current through here have to be the same. So the current right through here is 2 amps. Hey, that helps out because now look. If I was to hook up a voltmeter between between Y and Z, what would it read? Well, V equals IR for this location by the 4 ohm resistor.
Times the current of A1.
Ah, so what is my current through the 4 ohm resistor? 2. What is the resistance of my 4 ohm resistor? 4. So what is the voltage drop? 8 volts. So now I know that the voltage between Y and Z is going to be 8 volts. And I know that that's going to be the same as for here and here, right? So those are both 8 volts. All right? So, by the way, this is also 8 volts, right? Because XY and YZ are the same voltage difference, right? Same magnitude. Okay, so let's go over here. I still want to know what this current is. Well, V equals IR for this spot.
You know the current there.
I know the voltage drop here because that's from green to purple, which is
Same as that.
same as that, which is
8.
8. So I know that's 8 volts. I want to know the current there. And what's the resistance there? 12 ohms. Right? So my current will be 8 over 12 or 4 over 6 or 2/3 of an amp. Is that right? 2/3 of an amp. Now let's use Kirchhoff's rule here. We could figure out this current right here by doing the exact same equation, V equals IR, where the voltage difference would be that same 8, and our resistance would be 6, and we can find the current. But we could also do this. What's the current coming up this way? 2. And then how much of it goes this way?
2/3.
So how much is left to go this way?
4/3.
4/3. So I know that the current through this one must be 4/3 of an amp.
Okay, it's 2
Oh, do you use significant figures?
You can do this in decimal form if you like, and you would just do that as what, 0.67 and 1.3. That's fine.
We don't have to do the million.
Now, if all the numbers up there were listed as a couple sig figs, then your answer should be a couple sig figs. I had somebody on the test that we just took answer one of the questions, and they had 47,326.54321 for their electric field strength. Okay, yeah, you got a point taken off for that because that's excessive sig figs, right? Okay, so they just need to be reasonably close. Now, if it gives you actual data, like in a data table, then you can use whatever the sig figs they have. Okay?
So
All right.
You put it like a milliamp.
If you want to put it in milliamps, you can. Just make sure you put your proper units down. Okay? Sure can. Just make sure the units, because if you don't put the proper units down, then they'll assume it's the wrong unit. All right? What's that? College Board cares about sig figs in general, yes. I'll be honest with you on the exam, as long as you don't have excessive sig figs or excessive rounding on a normal problem, you'll be fine. So like if there's 2 or 3 sig figs in the problem, as long as you're 2 to 4, you're going to be fine. However, if they give you a data table with actual numbers in it, like from an experiment, then whatever the sig figs they have in that experiment, that's the sig figs you need to have in your answer. Okay? They're very reasonable about it. Okay. Questions? How we doing? We doing okay?
Yeah, we're somehow surviving.
All right. Let's do this bulb problem that you're talking about in your e-homework. Okay, before we do the bulb problem, let's write down all those, like the rules and things that we have at our disposal. We have V equals IR, technically delta V. We have power equals IV, that's delta V really, or I squared R, or V squared over R, that's delta V really. We have, if it's series, we have that the current equals the same everywhere, and that the delta V's around the loop should add up to whatever the EMF of the battery is, right? Does that make sense? Whatever's supplied has to be totally consumed. So you'll have a bunch of little delta V's as you go along through there. Each little resistor will eat up some of the current, some of the voltage until you've consumed all the voltage. And then the last thing about this is that the resistors in series equals R1 plus R2 plus R3. All right, in parallel.
Mechanism for it.
So it's there simply to keep me from writing all over the board.
Do that.
No, they're doing in pre-AP physics, they're doing waves. In parallel, the delta V equals the same for each line. All right, for each line in the parallel. And in parallel, the total current equals the current in line number 1 plus line number 2 plus how many different parallels pieces of the circuit you have. And then resistors. Resistor in parallel add up as reciprocals. Resistor 1 plus resistor 2 plus resistor 3, so forth and so on, right? And then we have Kirchhoff's rules. And Kirchhoff's rules we kind of really talked about already, but conservation of charge, which is the current that goes in equals the current that goes out of a node or a junction.
That's not the
And then Kirchhoff's rule says that you can, the sum of the delta V's in a loop all add up to be 0 as you go around any closed loop. All right? So those are all the things that we have at our disposal. Now, one last thing I want to talk to you about that you have at your disposal. Since you have these ways of adding the resistors up, one of the tricks we have is to take our complicated circuit and then simplify it down to a simple circuit, figure out what we can from that, and then rebuild it back out, right? So, one of the tricks is to take your complicated circuit, simplify it to simple circuit so you can find out the total current through the circuit. Okay?
And then you can go from there.
And then you can, once you know that, you can work your way back out, piece by piece usually. Okay? Right, so it's kind of like a big puzzle. Okay, what's the bulb problem?
This one right here.
Problem number, which one?
20.
20. Ooh, this one's hard. You probably missed this one.
First time, yes. So I stopped. First 2 times.
Okay, so we have it says a voltage source. So I'm going to do a battery. And you got a bulb here, and you got a bulb here. And there's the way it begins. And if it begins like that, it will look like this. Red,
Redder.
something in the middle, and then violet. All right, now, it says 2 identical bulbs, A and B, are connected in series with a constant voltage source. Suppose that the wire is connected, suppose A wire is connected across bulb B as shown. When the wire is connected across B, bulb A will do something. Let's figure out. So if I connect a wire from here to here, oh no, what is that wire called?
Short circuit.
It's called a short circuit. Here's what a short circuit does. You see this? Purple. You see this? That becomes purple. So what happens to this bulb?
No voltage is going.
Yeah, it goes out, right? Because the voltage on both sides are now the same. You've bypassed the bulb, short circuit, okay? What you've really done is you shared the electric potential from this side to that side, thereby eliminating the possibility of current through this device. Okay? So now the circuit has gone from what it was before. Let me redraw it what it was. And then let me draw the new. It was like this. And now the circuit becomes this. Hey, who's messing with the light?
Short circuit.
I'll short circuit you.
That was a good movie.
Short circuit? Man, you're going way back for that movie. All right.
This table is in it.
Hey. EMF here and EMF here, are they the same?
Yeah.
Resistance here and resistance here, are they the same?
No.
Ooh, what happened to the resistance?
It went in half because you have 1 volt left. Assuming the volt is.
It's greater in the first one. It's going through a source stage. Yeah. Come on.
The resistance of the whole entire circuit's gone down, right?
Uh-huh. The
How much down?
half.
It's 1/2 of what it was before. Half the total resistance. Right? If the resistance gets cut in half, if my original current is I, what happens to my new current?
Goes at. Wait, hold up. Twice? Should go.
Okay. V equals IR.
So 2 times.
If I cut this in half but keep this the same, then that's going to have to double. So now I have twice the original. Okay? twice the current. Okay, now look. If I take this bulb, and now I'm shoving through twice the original current. Now this is for the entire circuit. Okay? Now let's just talk about the bulb. If I talk about the bulb, when I double the current through it, have I changed the voltage difference across it?
No.
It's, ooh, I have, haven't I?
Okay. Well, isn't that what caused?
Because you can't turn through this.
Okay, so what's happened to the voltage?
It's changed.
It's double.
The voltage has doubled. So the delta V for the bulb is now twice as big as it was before, right? The current's been doubled because the delta V has been doubled, right? What has the resistance of the bulb changed? Or is it still the same bulb?
It's still the same.
Okay, so that's still the same. Now look, P equals IV, P equals I squared R, P equals V squared over R. For the bulb, if I double the current and I double the voltage, what happens to the bulb?
4.
I get 4 times the power. What would 4 times the power mean for a bulb?
4 times brighter.
4 times brighter. Because now it's consuming 4 times more energy, and in general that means, assuming a linear bulb, linear distribution for the reaction of the bulb, that means it should be 4 times brighter-ish, somewhere in that range.
Brighter-ish.
Okay, now look right here. Let's check to make sure that's true. If I double the current and I keep this the same, it's still 4 times. If I double the voltage and I keep this the same, it's still 4 times. So no matter how you slice it, that bulb is going to be 4 times brighter when you short circuit out the other one.
That's a very.
Which may cause it to burn out, so it's just...
Now it could mean that that bulb would burn out. Now some of you have experienced this. We just got through with Christmas holiday. You might have Christmas lights up, and that Christmas lights, there's a warning on them. It says that you should not have too many of the bulbs burned out. Okay?
That would leave less resistance.
Yeah, because if you have too few of those bulbs consuming the electricity, in some of the ways they're wired up. Not all the bulbs or the string of lights are wired up the same way. Okay, but some of
if
them.
you take out the light, the whole thing goes out.
Yeah, some of them, if you take out one light, the whole thing goes out. What kind of circuit is that? If you take out one light, they all go out? Series. What happens if you take out one light and none of the other ones go out, then it's in all totally parallel. Do any of you have the light bulb sets where you take out one and a section goes out?
Yeah.
Yeah, what kind of circuit is that?
Combination.
It's a combo. It looks like this. It's a bulb, and a bulb, and then a bulb, and a bulb, and a bulb.
It's like a bunch of duck bills.
Face.
Duck bills.
So if this bulb goes out, this line goes out, but these lines don't go out, right?
Is that the kind of lights that like they flash in sections?
Now, yeah, now different sections of the string will flash at different times. They could do that this way by having a flasher bulb here, here, and here, and so they'd flash at different times. By the way, those flasher bulb things, what they are is they have a connection inside that when it's a bimetallic strip usually.
So it just
Yeah, so what happens is when that is connected across, it gets hot. When it gets hot, it expands and disconnects. And then when it cools off, it goes back to its original shape and connects and then reheats up, so it flashes it on and off. So you'll notice sometimes when you plug those bulbs in, they won't flash for a long time until it gets all warmed up. And then after that, they'll start to flash. Okay, let's talk about this new and terrible thing called internal resistance. Okay? All right, a battery. You take the battery out, you look at the battery, and the battery will say on it that this one is 1.5 volts. My response to them is, liars. Lies. Okay, this is only a 1.5 volt battery right now. When you plug it in your calculator, it's no longer a 1.5 volt battery. All right. Internal resistance goes like this.
It's a song.
You have a battery. Okay, the battery has a chemical reaction inside. And the chemical reaction inside is what causes the charges to move from one side to the other, creating a high volt on one side and a low volt on the other side. Consult your chemistry teacher for further details of the chemistry that's involved. Okay? Okay. Go to electrochem.
Never. Not again.
Not again, come on.
Chemistry is evil.
Have you studied that in chemistry? Yeah, battery?
That was last
Chemistry.
All right, now, the deal is this chemical reaction does not happen instantaneously fast. Okay? So, how does that affect us? Well, that affects us, it behaves as if there is resistance in the circuit. Okay? So the battery, we draw it like this, but in reality, what happens is it behaves as if it has a little resistor inside. Okay? So we call this our EMF of the battery. The EMF of our battery is what it's listed as. But it behaves as if there's a little resistor inside. Okay? Now here's the deal, everybody. When the battery begins to die, what's happening is the chemical reaction is wearing out, it's being used up, and so it takes longer and longer for it to build up this potential difference if you have it hooked up to something. What it's behaving as if this internal resistance is getting higher and higher and higher. Okay? If you take a dead battery, just take a dead battery out of your calculator and you hook it up to a voltmeter and you read it, it's still going to read 1.5 volts. But then when you put it in your calculator, it ain't going to do anything. Okay? Let me show you why. Okay, if I hook this up to an external resistor, some device like your calculator, that has a resistance R. Now, look, if we're going to color this circuit, look at what the voltage is like now. Where's it red?
Right there.
Right there. Where's it violet? Right there. So what the heck's that? Orange, because I had it in my hand. It's not red.
Green. It's definitely green.
Definitely green. If it's nearly a dead battery, then yeah, it would be blue.
Doesn't work.
It doesn't work. Of course it works. You didn't hook it up right. You just destroyed your calculator.
Daniel.
You don't even have it plugged up to the
No.
All right, everybody.
I told you about
Here's the deal. Our battery, which is supposed to be 1.5, where's 1.5?
Between the resistor and the...
There.
Oh. So if you didn't
So what actually comes out?
something else.
Something else. Okay, we call that terminal voltage.
Maybe they definitely.
What's listed on your battery is the EMF, 1.5 volt battery. Okay? But what comes out is not EMF. What comes out of a real battery is terminal voltage. Or sometimes they call it terminal potential difference.
Get it?
Terminal voltage. Okay? We got terminal voltage. What the heck is the terminal voltage?
The voltage difference at the terminal?
Okay, well it would, if we use Kirchhoff's rule, remember Kirchhoff's rule about voltage? If we start here, we work our way around, we would add volts here, right? Then we would take volts away here, and then we would take volts away here, and that would take us back to where we started at, right? Okay. Now let's only use Kirchhoff's rule just for a section, just for the battery. So when I go from here to here, does everybody see that my voltage across the terminals, my terminal voltage will be the EMF of the battery
Plus IR.
minus whatever I lose here, right? Okay, now how do I find my delta V right here?
Current produced.
That's going to be I times little r, right?
That's what I meant by it.
And it's going to be a drop in volts, right? So minus I, the current coming out of the battery, times R. There's your terminal voltage. Told you it would work. All right, here's your terminal voltage, everybody. Shh.
He's not doing it.
Terminal voltage. Hey, why can't they just tell us what's the terminal voltage of the battery?
Because they
Since
don't want
the
to
internal
They want to
resistance
changes.
There's two reasons. Number one is as the battery runs down, this internal resistance gets bigger. So that's problem number one. Problem number two is, what's the current going to be? Ooh, 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 ooh. Somebody's onto it.
Over the resistance in it
There's my simplified circuit. EMF. And what's the total resistance of my circuit?
R plus little r.
Big R
Plus little.
plus little r. Oh no. So my total current going through the circuit
Because E.
is going to be V, which is EMF, over the total resistance, which is R plus R. Oh no. We don't know what the total current going through that battery is going to be. It depends on what you're hooking up to. Does everybody see that the manufacturer of the battery does not know what you're going to hook your battery up to? So they don't know what kind of current you're going to be drawing through your battery. So they don't know what the terminal voltage is going to be. Right? So they simply cannot tell you what it's going to be. So all the best they can do is tell you what the best voltage, the EMF of the battery, is going to be when it's in the package and you're not using it.
No, don't change.
All right? Now, I want you to look at this another way. You see this?
Is that all right?
If I put an ammeter right here, and I put a voltmeter right here, by the way, this voltmeter is going to read the same as if I put a voltmeter on both sides of this battery, right? Orange to purple. So it's going to read the terminal voltage. So this is going to be the terminal voltage. Voltage terminal. And this is going to be the total current, right? That right there. Total. All right? Hey.
Yes.
What if I was to graph voltage, the terminal voltage,
By
versus the current that comes out of this thing?
total current.
Mhm.
It's a.
What's it going to look like?
A line going down.
Ooh, somebody got it quick. Hey, let's use our little math magic skills here. Look at this. This is my y-axis. This is my x-axis. Do you see it? There's my slope. And there's my y-intercept.
What?
You need a graph voltage.
Yeah. So what's this point right here? It's going to start right here. That's the EMF of the battery. Which way is my slope going to be? Positive or negative?
Negative.
Negative, right? So it's going to go like this. And right here, the slope of that is the internal resistance of the battery. Cool.
Cool.
It's actually quite cool. Because it gives you this magical point right there.
Okay, but that's V terminal, right?
This is the no, hang on.
X-intercept.
This is the terminal voltage. When is the only time you get the actual EMF of the battery?
That's V.
When you don't use it. When there's no current coming out of it, you have an EMF of your battery. Once you start to use your battery and draw current from it, notice that the terminal voltage gets less and less and less until you get a maximum. If I took this battery and just did this, and I hooked jumper cables from one side to the other that have no resistance, does that mean that my battery will produce infinite current?
No.
No, it won't produce infinite current. And here's why. Because all of the voltage will drop right here across that resistor. That little resistor will eat up all of the all of the current. Sorry, all the voltage. Eat up all the voltage.
Plus,
And your battery will get really hot.
and your cable will get very hot.
And the cable could get really hot too.
So which one explodes first? the battery
Which
or
one
the cable?
explodes first? I don't know.
Insanity.
Hey, everybody right here? This is the maximum current that the battery will output. Shh. Maximum current the battery outputs. Now watch what happens. When the battery gets older, the internal resistance gets bigger. What does that mean for my graph?
Goes
It's
down.
great.
It gets steeper.
So if you put time into it, it's like a little slope.
Yeah, so what happens, it starts like this. So if you want a battery that produces more current, you have to have less internal resistance. Or a higher EMF, one of the two, right? Okay, as your battery gets older, the internal resistance gets bigger and bigger and bigger. Eventually, you'll cross a magical spot here where the battery cannot produce enough current to run your device. We label that as when the battery's dead. The battery is not dead, it's just not able to output enough current to run the device. Okay?
You just
Now-
don't want to admit that you killed it.
That's right. I killed it. It's still alive. So, in your calculator, because your calculator runs on such a low amount of current, your batteries actually last a long time, which is why you're able to put these little dinky batteries in here, okay? Because they have very little chemical reaction in them, because they're tiny, okay? The original calculators were run on AA batteries instead of AAA, or sometimes even bigger batteries than that, because they had glowing red screens. You ever seen one of those? The really old ones with a glowing red screen? Those suckers consumed energy at a prodigious rate. And so you had to have bigger batteries. Okay? More chemical reaction.
Here's your calculator, here's the battery.
If you ran this thing on, instead of 4 AAA batteries, and you ran it on 4 D cell batteries, you would never change the batteries in your lifetime, probably. Because it has enough chemical reaction inside it. Okay. All right. There's a couple of problems in your e-homework, and as long as you can spot,
Back in the third grade.
as long as you can spot how the circuit is really set up, the problems are not that hard. So let me show you a couple of things that'll help you out. All right. So get out your e-homework, everybody. Let's take a look at it real quick. There is one problem that looks like this.
I'm just saying right here.
Okay? And in one of the problems it looks like this,
That's a switch.
and then in the other one it has a switch, and then one of the switches open.
And then
Okay? All right, now, everybody, when the switch is open, let's just color it quick. Here's red. Here's violet. Okay, what goes here and here?
other colors.
Other colors. Are those two colors, do they have to be the same?
Depends on the resistance.
Yeah, it depends on the resistance. They do not have to be the same. One of them could be yellow, and one of them could be, I don't know, blue. All right, or green. What do I do with my green? Here. Greenish. All right? They do not have to be the same. So let's redraw this circuit. If we redraw it all boxy, it helps us out sometimes. So what does this look like? It looks like this.
Oh yeah, I know it helped me when I didn't get this. I was like, what? I'm trying.
If you redraw it all boxy, it's a little bit easier to spot. What do I have? I got a series here, and a series here, and then these two series are in parallel. But you have to add up the two series first before you add them in parallel. Does that make sense? The reason why I can't add this one to this one and this one to this one in parallel is because you can only add things in parallel if they have the exact same,
You forgot
Potential
about the
difference.
switch.
huh?
It's a switch.
You don't need it. 'cause
They don't need it.
right?
Do you see that the voltage here and here and here and here are not the same? So I can't add them up in parallel. However, do you see that the voltage from this spot to this spot is red to purple, and from this spot to this spot is red to purple? That means this line is in parallel with this line, but this line is in series, so I can add those two together in series, these two together in series, and then I can add the two lines together in parallel, right? Okay, now, what if it's redrawn, but now the switch is closed? When the switch is magically closed, what happens?
You have a short.
I have a short between these two. These two must be the same electric potential now. And so I'm just going to magically make them yellow, just because it doesn't really matter. Okay, so now it's all yellow. So wait a minute. How does that change our boxy drawing? In our boxy drawing now, it changes because now I have a connector here. Okay, let's make it a little more visible. It's like this. Does that help out? Yeah, now it's easy to see, right? Do you see now that this is red and yellow, and this is red and yellow, so these two are in parallel? And this is yellow and purple, and these two are in parallel? But do you see that this top one here and this top one here are not in series now?
Yeah.
Because the current that goes through here
It's not.
does not all have to go through there. Some of it can go this way, right?
Or vice versa.
Okay.
Okay.
Or vice versa.
So in this case, since when you close and open the switch, you also change net resistance, wouldn't you?
Yes, and so please be careful. When you close that switch, you've changed the essence of the circuit. Therefore, you haven't changed the EMF, but you have changed the resistance total. So therefore, you've changed the current total. Okay, the total current through the battery is now new. Right? It's now different. Okay, what we have to cover yet is we need to talk about motors and bulbs and capacitors in a circuit. But I'm going to stop and let's just work a practice problem real quick.
Oh my God, Mr. Brewer, yeah.
Like shifting.
All right, everybody. Here's the problem we're all going to work in class. You're all going to work it for me right now. I want to know, what's the current right here? I want to know what's the current right here. I'll call that I1 or current 1 and current 2. And then I want to know what the voltage will be right here and right here. I'll call that voltage 8 and voltage 4 for our 4 ohm and 8 ohm resistor. All right, go. Okay, if you're going to simplify this, what's the first thing you can do to simplify it? Why can't I add that to that? They don't have the same voltage, right? Okay, because this is red, this is violet, this is blue, this is green, and this is yellow. Yeah, I left my orange over there. Alright? So I can't add this 4 to this 6 because they don't have the same voltage, right? Okay, so I can add these two together. Hey, by the way, can I add this one to this one? Yes, I can. Are these two in parallel?
Maybe.
But you have the resistors in the
It took you so long, Colin. Gosh.
I was negotiating.
There you go.
People.
Negotiate.
Are these two in parallel, yes or no?
Yeah.
No, why not?
Because they're connected battery.
Because they don't have the same voltage, right? Are they in series?
Yeah.
Wow.
Does all the current that goes through here have to go through here?
Yes.
Yeah, so I could add them up in series if I want. Most students won't because they find that, I don't know, troublesome. So let's do it this way. I'm going to add that up. So this is 6, this is 6, and that's 2. Okay, what do I add next? These two parallels? So I end up with, oh, sorry, that's 1. That's now 3 when you add these two in parallel. And that's 1.
That's a grand total of
12 volts, 12 ohms. So what's the total current?
1.
1 amp.
Yeah.
Okay, so now I know that this one will read 1 amp. Okay, now let's use our brains. This reads 1 amp. What will that one read?
0.5.
Why a half?
Because it's all the same resistance.
Because that's 6 and that's 6, and so it's going to split evenly, right? So this will be 1/2 of an amp. That means over here it's 1/2 of an amp. So that means that right here, I can already figure out what this voltage is going to be, because this is V equals IR for my 4 ohm resistor. That's going to be a current of 1/2 of an amp, and that's a resistance of 4 ohms. So I get a grand total of 2 volts. So that one's 2 volts right there.
And that one's 1 amp.
And that's 1 amp, V equals IR. 1 amp going through here, a resistor of 8 ohms. So I get 8 volts here. All right? There you go.
Hey.
If these are 3 bulbs, all identical bulbs, will they all be the same identical brightness?
No.
No. Those two.
Wow, that was easy. Which one's brightest?
The one top.
The first one?
No, the one closest. Series with the battery.
The one on the left? Boo.
The Marcos came in.
Man.
The Mexican in the bed. Sorry.
All right.
Assuming they're both of the same resistance. then
Okay,
B and
here's
C
the
would
deal,
be-
everybody. Power equals IV equals I squared R equals V squared over R. Okay. The current, if you want more power, you need more current, right? So which one gets the most current?
First
That one, right? It's the total current. Okay, how do these two compare?
split. They have no
Okay,
current.
they should get half the current each, so they should be less bright. In fact, they should be half the current means they should be 1/4 as bright. Right? Because it's squared. Alright. So when you're looking at bulbs, look for highest current or highest potential difference. In either case, that shows you which one's brightest. Okay? Because the resistance of the bulb should all be the same if they're identical bulbs.
So, you know how light bulbs, when they sell them, they have both voltages and power, right?
Yes.
So that depends on the current, though, right? So they're
Right. Yes. In fact, oh shoot, I don't have a bulb sitting
don't
out
they
here.
technically not know what current you're running at? So then, is
Okay.
that voltage the minimum requirement, or what?
Yeah, we'll cover it next time, but, like, the thing is that they are telling you what the power of the bulb will be if you hook it up to the 110 volts it's supposed to be hooked up. If you hook it up to something else, it won't be that power. We'll talk about that next time. All right,